So we're going to look at equations of graphs of essentially polynomial functions. Okay, so this is the equation of some polynomial function. It's in what's considered factored form. Okay, and the factored form will help us essentially find what x-intercepts are. Okay, so this is our factored form. It's good because we can find out a lot of information from our factored form when it comes to graphing. There's a couple of things we want to know about these when graphing them. First of all is maybe what order this function is. So in other words, what degree the function is to. So this one here is technically to the power of 1. Okay? And this is to the power of 2. So if we were to expand this, and expanding would mean, you know, taking this away and going through distributive property with all three of these, we would end up with eventually an x cubed. So that means we have a cubic function. Okay? And the a value, or the value in front, and assuming that the x's are all positive, which they are in this case, is technically the value of 1. But what's important is it's positive. So we want to know a couple things about these types of functions. So let's put a quick graph up here. So I see 1. Okay. So in a cubic function, what's going to happen if our a value is positive, the normal cubic function, which is is usually written as y equals x cubed. Okay, we know we have some form of this function. That function, if positive, comes down from this angle, crosses our origin when tangent to it, and then comes back up again. Okay, so it makes this type of shape. So this is a positive cubic function. If we had a negative cubic function, it would just do the opposite. It would come down from here, cross at the origin, and go down. This would be essentially the function of y equals x cubed, sorry, with a negative in there. Okay? So we know we're going to have some form of this function here. But what's important is we want to find out exactly which one it is we have. We'll use these to plot our x-intercepts and then graph from there. So what's good is because we know it's positive, we know we're coming from this area here. We're coming from quadrant 3, which is important. Okay? If it was negative, we'd be coming from quadrant 2. Okay? I'm just going to erase what we have up here so that we have a nice clean graph to work with. So what we need to notice is if we want to find x-intercepts, the idea is that when we are looking for x-intercepts, we're looking for when our y value is 0. So algebraically, essentially that's our f at x. So if f at x was equal to 0 and we had x minus 1 times x plus 2 squared, and we had to create a y value of 0. What that means is one of these brackets is essentially going to be equal to 0. We just don't know which one. So we're going to test for all of them. Okay. Now technically there are 3 brackets. We have another x plus 2. But because it's identical, we write it as 1. So we really only have to test the 2 of them. What we're going to do is from this point is we're going to split the both of them up. Okay. And we're going to set both of these brackets equal to 0. So we have 0 is equal to x minus 1. And in this bracket, we have 0 is equal to x plus 2, and all of that squared. In the first one, it's very simple to find out what x is. When we bring 1 over, it becomes positive. 0 plus 1 is 1. So one of our x-intercepts is the value of 1. In our other one, we have to get rid of this power of 2. And then in that case, when we bring that over, we would square root, right? Well, what would the square root of 0 give us?
0.
Still gives us 0. So now we're left with 0 is equal to x plus 2. So really, we can kind of drop those. They aren't that important because whenever we find the third root, the square root, the fourth root of 0, it's always going to be 0 in that case. And then from here, we're going to be left with x is equal to negative 2. But what is important is what this squared is going to do to our function. Okay? So we know we have 2 x-intercepts. One of them being at positive 1. So we have one x-intercept here, and the other one being at negative 2. Negative 2 is back here. Okay. Now we said that in this function we're going to be coming up, and then coming up from quadrant, where are we? 3, sorry. Because this is a positive function, we're coming up from quadrant 3. Okay? Now, what's important about that is what's going to happen is we need to be coming up from here, and we actually need to take off in that direction after. Okay, so we have to have some effect of this. The problem is with these x-intercepts, if we cross directly through them, I end up down here. Okay, and that's where this squared comes in handy here. This squared tells us that we actually, when it's squared, we don't actually cross that intercept. We become tangent. We have a parabola type effect, okay, which is essentially like our x squared functions, which is a parabola. So we become tangent to it and then head back down in this direction. Then eventually, at some point, we come back up again, heading out this way. And at this x-intercept, we do cross through because it's only to the power of 1. Okay, so essentially when we have powers that are even values, we're not going to cross our x-intercepts. So whether it's squared, okay, or quatic, which essentially becomes like that, or to the power of 6, we're not going to cross at those points. But when we have odd numbers like 1 and 3, we are going to cross through. Like in this instance, we cross directly through. If it was cubic, we would kind of become tangent and cross up like that. It'd be that to that essentially effect. So we're just drawing a rough sketch. In this case, what's happening is we're coming up, we're touching, coming back down, and then crossing through again. So this is a form of a cubic function. But we can find out more information from this. We want to know what our y-intercept also is to help us with our sketch. Okay? Now our y-intercept is going to be the constant in standard form. So when we expand everything, whatever the last constant term is at the end, that's going to give us our y-intercept. Well, instead of doing all the distributive, what we can focus on is just multiplying the constant values, so the numbers by themselves. Now it might be easier to look at this, we'll use the same one, f at x, in a more type of expanded form with our factored. So let's say we go x minus 1, x plus 2, and then we're going to expand it to the x plus 2 again. I'm not going to keep it squared there. And the reason being is because I want us to focus on multiplying these numbers by each other, because that will be what our constant term is at the end. So negative 1 times positive 2 will give us what?
Negative 2.
Yeah. And negative 2 times positive 2 will give us?
Negative 4.
Negative 4. Okay. So actually our y-intercept is at negative 4, which means we're going to change our type of graph in the middle here. Our x-intercepts stay the same, and we are affected at them the same way. Okay. But with our y-intercept, we're either turning beforehand and coming up, or there's a chance we're coming through turning after and heading up. Okay, we're not quite sure which one it is yet. Have they talked to you about how to find that stuff?
No.
When it's turning? Usually that's done in a calculus course. And we would use derivatives to find that quickly. So to draw a rough sketch, there's nothing wrong with saying this. What happens is it comes down at negative 2, it crosses at 4, and then comes up and crosses at 1 again on the x-intercept. This is a rough sketch of what we are looking at in terms of this polynomial function. So here's another example here. This is actually a rather large function. And the first thing we want to discover here is kind of what degree this is to. And the way we do that is essentially just add up our exponents. So 1 and 2 is 3, plus 3 is 6, 4 is 10. Okay, so this is a 10th degree function, which means it is an even value. So since it's positive, we should be coming down from this area. And then the degree of the function will actually tell you how many terms are involved. So actually, let's jump back once more. Because we discovered this was the degree of 3, okay, we had changes in directions, 2 changes in directions, and it goes up. You'll have one number less in terms of change of direction. So if it's to the power of 3, we'll have 2 changes of directions. If it's to the power of 4, for the most part, we'll have 3 changes of directions, unless it's kind of really a flat one here. But usually if it's 4, you do something like 1, 2, 3 changes, and you come back up that way. It makes a W effect. Okay, so this is the power of 10, which means we come down and we go 1, 2, 3, 4, 5, 6, 7, 8, 9 changes in directions. We have something like this, but we really don't know how high the peaks and the troughs of all of these are going to be. But we should come down from the second quadrant and then be heading in a positive direction in the first quadrant again. Okay, our x-intercepts we can easily look at. Now, I could set them all to equal to 0, but we can pretty much look at them since they're relatively simple. What is one of the x-intercepts going to be?
1.
Positive 1.
And negative 1.
Yeah.
2.
Positive 2.
Negative 2.
Negative 2. Those are going to be intercepts. What's important are the degrees of all of these, and we're going to talk about how they affect what we're drawing. So one of them is going to be at 1. Okay, so we have 1. It's at the power of 1. We have another one at negative 1. So crossing over here. We have another one at positive 2, which is here. And we have another one at negative 2, which is here. Okay? So we have all of these values here. And the one other thing we really do want to figure out is what our actual Y-intercepts going to be. Okay, and like we said before, in that case, we just focus on these. Now, I could write them out like I did before, or I can apply the powers to these specific numbers in here. Okay, because we know when we multiply across, that's what they'll be. So this power won't affect anything. This will still be positive 1. This will still be negative 1. Negative 2 to the power of 3
8.
is negative 8. Okay, and positive 2 to the power of 4 is 16. Okay, so now we're looking at numbers. I'll just write them all out here. It's negative 1 times positive 1 times negative 8 times positive 16. Okay, well, I'm going to have a positive value. I have a negative times a positive, which is a negative. Negative times positive, negative. 2 negatives is a positive. So we have a positive value. And when I multiply all those together, we discover that it's going to be 128. So we have a y-intercept that's way off this chart. Okay, we'll just kind of throw that in there, 128. So let's talk about each of them. This being negative 2, this being our negative 2 here. Well, we know that's to the power of 4. So essentially what's going to happen is this one's going to come down, and it's going to go flat here and then come back up. Okay? At negative 1...
Doesn't that come from the third quadrant?
No, because this is a power of 10.
Right.
So because it's a power of 10, we should be coming from quadrant 2 and finishing in quadrant 1, heading up in this direction and coming down. Almost like a parabola type. Think of a parabola being squared. It would come from quadrant 2 and then up to quadrant 1. If it's an odd number, it'll come from quadrant 3.
Okay.
Does that make sense?
Mm-hmm.
Yeah? Okay. So it comes up. Our negative 1 here is squared. So this is going to change direction somewhere again and have a squared-like effect again. We don't know how high these are. We would use our calculus to find out what that is. We also know we have a y-intercept way up here. So essentially this takes off way up here, maybe passes it and comes back down again. Our next one being positive 1 is a power of 1. So we know we're going to actually cross right through at 1, okay, because it's the power of 1, so we cross right through. And then finally, our positive 2 is to the power of 3, so we know we have a cubic type of effect. It comes up, goes flat, and then takes off again and ends up. So we ended up in our right quadrant, all right? We came down from quadrant 2, ended up towards quadrant 1, and all of our effects seem to have worked out. Our turning points were unknown, but what's important is we know how each of these affect our X intercepts in this case.